Gehring, and I'm going to tell you a bit about the simulations I did on this rocket here. This rocket's called OORR Rocket, and Rocket Club just built it for testing various mechatronic systems. The thing about having a rocket for testing various systems is that the systems might shift around the center of mass, and they might even influence the flow field around the rocket depending on where they are. So you want a rocket that is very stable so that those adjustments don't mess it up. So in order to optimize the stability of this rocket, um, for this project, I looked at different fin lengths, or fin heights, so that the distance from the edge of the rocket to the tip of the fin, um, and I wanted to see how big can you make the fin without causing the rocket to oscillate in an unstable manner. Um, and in order to figure that out, I needed to run a bunch of simulations to assemble tables of coefficients of lift drag and moment versus angle of attack. Um, so I'm going to sort of walk through how to put together those simulations now. So here's Workbench here. We'll start with the geometry. The geometry is imported from SolidWorks into SpaceClaim, um, and that'll take a moment to start up here. Okay, so here's SpaceClaim, and you can see this is the rocket geometry right here that was imported originally from a SolidWorks file. It's a SolidWorks part file. The You can see it's just sort of a very basic geometry. It's pretty accurate to what the rocket actually is, but all the like screw holes and stuff like that are missing. So it sort of simplifies the meshing a bit and make sure that there aren't any little cavities. Um, then next step was to generate this enclosure here. The enclosure, yeah, you can get to the enclosure tool here in the prepare tab. So you click on enclosure, and it allows you to define a box around um, your object of certain dimensions. So you can see like it extends out in the x direction by 25,000 millimeters on one side. So that would be this side, and 7,500 millimeters in the other direction. So that's on this side. So that allows you to build this computational domain around the object pretty nicely. You'll notice that I put the rocket offset from the center of the enclosure here, and the reason for that is so that it's easier to capture the entire wake coming off the rocket if there's an angle of attack. So the idea would be to have the inlet on this face here and this face here. So the air is coming in like this, then it hits the rocket, and then you end up with a wake out here. And there's more room out here than over here. And then the same strategy goes for these bodies of influence. So the bodies of influence are just generated by sketching on on a plane and then extruding in either direction, but they're extruded more in the direction that the wake's expected to go in, so that there's more room for the wake. And you can't, so you can see where the rocket is there. And then after I generated the geometry, I went through and named things. So the most important parts are the inlet. So these two faces right here, closest to the rocket, are the inlet. Then the outlet is these two faces over there, and the walls are the top and bottom faces of this enclosure. And those walls are going to be free slip boundaries, um, because in reality the rocket doesn't fly in a box. Then all these other labels are for different parts of the rocket, because I wasn't sure if I was going to want to be able to define the surface mesh differently for the different parts of it. One thing I've noticed that these named selections are not actually on the geometry I imported. Like they're not on this thing. They still exist if I deselect that. They're on the surfaces of the enclosure that interface with the surfaces of the original CAD model, because essentially the rocket doesn't really exist for the simulation. It's a void. There's nothing there. What matters is the enclosure, because that's where the air is. All right, so I think that's it for the setup here in SpaceClaim. So we can close out a SpaceClaim, and then we're going to go over here to the mesh. So the way this is set up is there's a let's see, a geometry block here, and then a fluent with fluent meshing block here, and the geometry is piped into the mesh. So that's what's already set up down here, but that's how you set it up. And then for the geometry, you import geometry, and then you'd select your SolidWorks part file here, and then you'd open it in SpaceClaim. If you just double click on it, it might default to one of these other things, which you could also use, I think, but I don't know how to use them. So I'm going to get rid of that. So now we're going to open up Fluent Meshing, um, and no, I don't want to update things because I don't want to have to wait around for the mesh to regenerate. I've been using 20 meshing processes and 20 solver processes because this is a 12-core CPU and it can run 24 threads simultaneously. So you can see here the mesh size is around 16 million cells. Okay, so the workflow here, I'm not going to change it, but it's set to watertight geometry. You can adjust that over here in Workbench before you open it, and also adjust the units, and set the number of processors and stuff like that. So if I look at this tree here of tasks that need to be performed is the default for this watertight geometry workflow. So the first is to import the geometry, and if you have it set up like this so that the geometry from this block over here is piped into this fluid meshing block, then when you hit import geometry, it'll automatically import the geometry. So it'll import your enclosure. And then under local sizing for the near field body of influence, I have the target mesh size set to 16 millimeters, and the type of the type of local sizing is a body of influence. That's the goal. And then for the far field body of influence, that the let's see, where is it? Not sure why it's not showing up in here. If I hit revert and edit, it would. But it's the far field is body of influence is a name selection, and that is set to have a 64 millimeter mesh size. And then for the rocket itself, I have curvature controls set. So the local minimum size is 0.5 millimeter. Local maximum size on the surface of the rocket is 8 millimeters. And the mesh should generate so that there's never any more than 3 degrees error on that surface. And then so this block right here generates the surface mesh, and the surface mesh already exists. But if we can look inside this thing. See. So here's the mesh in here is what it would have generated. So you can see this is up by the nose cone, and this is the tail cone of the rocket. And this is sort of looking at one of the fin mounts from the inside. You can see this down here where there's sharp corners. There's cells as small as 0.5 millimeter. Then for described geometry, I'm not considering the interior of the rocket at all. So it's only a fluid region that I'm looking at. It's only the enclosure minus the rocket essentially. And then for boundaries, all the parts of the rocket, so the fins, the nose cone, the tail cone, and the body tubes, lower, middle, upper body tube, are set to walls. And then the walls of the enclosure are set to walls, and then the inlet is set to a velocity inlet, and the outlet is set to a pressure outlet. And then update regions. So I'm not sure why it defaulted to these names. This is confusing, but fluid, for whatever reason, is the rocket, and it's set to a dead zone because nothing's happening inside the rocket. And then enclosure is the enclosure that we care about. That's where all the air is, and that is a fluid region. Then boundary layers. So along the surface of the rocket, you can see, we have all these thin layers stacked on top of each other. So that's what this is generating. And the way it does it is using this last ratio block. So the last ratio between like the width of these cells is set to 0.2. So it increases by 0.2 every time, or like between each layer. And then the first height, so like the height of these cells right up against the side of the rocket, are 0.5 millimeter. So this sizing is probably appropriate because the rocket's going very fast and the boundary layer is very small. So then you go down here and generate the mesh, and it's a polyhex core mesh, and the minimum cell length is 0.5 millimeter, and then the larger cells are about 0.5 meter. So you can see way out here already. So that's that, and I'm not going to regenerate the mesh because it takes forever. And yeah, so you can see there's much finer mesh. This is the near field body of influence. This is the far field body of influence. And then there's no mesh refinement along the walls, like the external walls of the enclosure, because we don't really care very much about them. There's just mesh refinement around the rocket itself, and that's the goal. So I'm going to close out of here. All right, so it's done loading the mesh. Um, so let's look here in setup. So for models, we have it set to this K omega turbulence model, and I left all the defaults because I don't know much about that kind of thing. And everything else is off. Then for materials, the only material is air. It's a fluid. The solid's not used anywhere. Zone conditions. So for fluid, the enclosure, and that's is the fluid. That's the air. As you can see, it's set to air, and there's no rotation going on here. Then boundary conditions, inlet. Here's the inlet velocity. The inlet velocity is parameterized, so you can look in here. It's set to this velocity magnitude parameter, and you can manage those parameters in a different pane. But the velocity magnitude is one of the two main input parameters. The other one is the angle of attack, and the angle of attack is used to calculate this comp vel x. Comp vel x is equal to negative cosine of the angle of attack, and comp vel z is negative sine of the angle of attack, and that gets you velocity coming in from this corner. So you get you get the right angle of attack you want. So we can go over to user defined. If you look in manage named expressions, you get these different values. So here's angle of attack. That's the input parameter that's defined. You can set that in Workbench. And velocity magnitude, same there. So that's set to 40 meters per second. And then comp vel x is set to negative cosine angle of attack, and comp vel z is set to negative sine angle of attack. Then these other things, CD out, that's the coefficient of drag in the direction of, like if you take it in the direction of flow. So if you take the drag force as the component of the net force on the rocket that's in this direction along the direction of flow, then this is the drag coefficient you get out, the CD out, and that's calculated from the coefficient of drag you get if you take for drag force to be in this direction, and also the lift force you get if you take lift to be in this direction. So essentially this is transforming the drag and lift, these two functions here are transforming drag and lift coefficient from the rocket frame to the frame of the air, the flow, the inlet flow. So that's what you're getting here. And it doesn't really matter which ones you use, but it's sort of more conventional for aircraft to think of drag being in the direction of flow and lift being perpendicular to the direction of flow. So that's why I calculated these. So that's their output to Workbench 2, and that's that. Then okay, we got, so that's the inlet boundary condition. The internal zone is just the enclosure. Nothing going on there. That's just air. The outlet is a pressure outlet. Gauge pressure is set to 0, and nothing else is happening with that. And then the walls, all these walls, so fin 1, fin 2, fin 3, body tubes, nose cone, tail cone, are all no slip boundaries. And then these walls are the walls of the enclosure, and they're free slip boundaries. So shear is set to 0. And then that's it for boundaries. The next thing you can do is if you set this to a transient solver, you can go into dynamic mesh, turn on dynamic mesh. You want layer remeshing and smoothing so that it redoes the mesh around the rocket as the rocket moves. And then you need a 6-degree of freedom solver to figure out where the rocket gets pushed around by the flow. And you can go in here and create the rocket. Mass the rocket's around 21 kilograms. Moments of inertia are here. Create the rocket. Okay, now if we go into create edit, we have rocket selected here, and the center of gravity location is negative 2.175 meters on the x-axis to begin with. Then it'll move, and the 6-degree freedom solver is turned on. Now this up here actually needs to be used to select all the surfaces of the rocket, but it can't right now because they're all split up into different surfaces, or like different name selections, so the fins and the body tubes and the nose cone and the tail cone. So I have a different simulation where they're not split up into different components. They're just all called rocket, and it's one name selection for actually running this dynamic mesh. So if you want to do the dynamic mesh, you need to make sure that maybe there's a way around it, but I can figure that out. So the only way I know to get the dynamic mesh to work is you need everything you want to move to be under one name selection, which I can't do here because they're all different things. But assuming that that was all of the rocket up there, it'd be a rigid body, and then you'd create it, and then it would show up here, and then you'd be good to go to run your dynamic mesh simulation. But I'll turn this off for now. Then reference values, it's kind of important to know what these are actually. Inconveniently, you can't parameterize these as far as I know. So if you're going to change the velocity and you want the coefficients to be calculated properly, you have to change this by hand. But it's set to 40 meters per second for the velocity. And then the area, this is the projected area if you're looking down the axis of the rocket. Um, Here in Workbench, where you can access the parameters, so if you go into the parameters tab, um, you can see here all the different parameters. So this is the velocity magnitude, and here's the angle of attack, and those are the ones you actually set, and then the other ones are calculated. So see these ones right here are the drag in the direction of flow, and the lift defined perpendicular to the direction of flow. And then this is the moment coefficient. Um, and then you can see I've got different cases for the different fin lengths, and then different mesh densities and stuff like that. A few interesting results I got. This is the animation from one of the transient simulations I ran. This is with time step 1e -5 and velocity of 100 meters per second and angle of attack of 10 degrees. And it's the same mesh I just described. So I'll just scrub through it because the video is actually very long because the time step's so small, and this movie player doesn't know how that works. But um, you can see it sheds a vortex, and then the flow stabilizes. Um, but throughout that time, there wasn't any uh, super huge changes in coefficients. You can see here's coefficient of drag, and this is right around when the vortex is coming off the fin, and you can see the coefficient of drag went from down here, average of 0.78 or whatever, up to around 0.81, which is maybe a 5% difference, but not super huge, which provides some sort of indication that hopefully it's a reasonable assumption to use steady state simulations to model this transient flow problem. Interesting animation here. This one is for the dynamic mesh simulation I ran, 6 degree of freedom simulation with 9-inch tall fins and time step of 5e -4. So this just covers about 70 milliseconds, but the fin does move a bit, which is interesting. It sort of provides it's a bit of a proof of concept of the whole dynamic mesh technique. But given that this took about 8 hours to run just this, and the time step isn't even that small, I'm going to need to find a beefier computer to do this on. But it is pretty neat that the fin moves. The results that are actually useful for flying the rocket right now. That's the series of steady state simulations at different angles of attack for the different fin heights. So you can see this script here pulls a bunch of data from a spreadsheet that was output from Workbench with a table of those coefficients for the different angles of attack. This is all for 40 meters per second. So you can see there are these different data points, and the curves are fairly linear for the different coefficients. These RF coefficients are the ones defined in the rocket frame. So CDRF is along the axis of the rocket, whereas CD is along the direction of flow. So you can see that CDRF is pretty much constant, whereas CD does increase with increasing angle of attack, as you'd expect. And so this data right here, and then interpolated values between these data points between 0 and 10 degrees are what's used as the input to this simulation right here, which uses an explicit Euler solver down here that's being updated down here. And you've got velocity, 2D position, and then angular velocity, and then angle, so like the yaw angle of the rocket. So we can run this. and that will give us, actually this is the results of several simulations. So this is just the result of the for the 15 centimeter tall fin, and you can see that the oscillations are damped. This is well, actually I'll hop over to a prettier graph with the same data on it. Where this is the wrong one. Here we go. So yeah, this graph right here, you can see this is where the rocket clears the launch rail. So when it's on the launch rail, its angle is constrained to 90 degrees, and then after that, it can pitch over into the wind, and the wind is set to positive 2 meters per second in the x direction for the simulation. So it pitches into the wind, meaning that it pitches counterclockwise, which is why we see an increase in theta here for all the different fin heights. And you can see that for the larger fins, it pitches over more because the lever arm between the center of pressure and the center of mass is greater. And then for the smaller fins, the 15 centimeter fins, it pitches over less. And then the oscillations are more damped for the 15 centimeter fins. Now, this black line here is when the motor burns out, and the motor thrust has a stabilizing effect on the oscillations. So after the motor burns out, then for these larger fins, the oscillations increase in amplitude. Now that makes sense because if you look at a rocket like this, and you consider thrust is in this direction, it's always along the axis of the rocket. If the velocity, or sorry, if the rocket has some velocity u in this direction, and then you've got some thrust here, applying thrust in this direction will always increase the velocity in this direction, which will, that has to decrease the angle of attack, because if you're increasing velocity along the axis of the rocket, then that's making the total velocity more in the direction of the axis of the rocket. And if the velocity is in the direction of the axis of the rocket, then there is zero angle of attack. So thrust tends to decrease angle of attack. So that is what we're seeing here. By increasing the speed of the rocket along the axis of the rocket, it decreases angle of attack and damps these oscillations. But then when the motor burns out, you don't get that effect anymore. And then drag afterwards, or drag defined in the rocket frame, which is relatively constant for small angles of attack, as we saw in these graphs here. The blue line here is drag in the rocket frame, pretty much constant for all the different fin sizes. So after motor burns out, drag is the force along the axis of the rocket. Before, thrust was dominating from the motor, but the motor's burnt out, so it's just drag now. And drag has the opposite effect. It decreases the velocity of the rocket in the direction of the axis of the rocket, which tends to increase angle of attack. And then lift has its own impacts on the stability of the rocket, and it depends on where it's acting, how far away it is from the center of mass. But this video is already very long, so I won't get into the weeds on that. What conclusions can we draw from this graph we have here? So the 30.5 centimeter fins are probably not a great choice. Over the course of 8 seconds, the amplitude of the oscillations doesn't get particularly large, but if the flight were longer, or the simulation ran for longer, they might get bigger. Also, it's just harder to be confident in the results of all these simulations for higher amplitude oscillations and higher angular velocities, because all these simulations assume that angular velocity is very small and angles of attack are very small. So that's probably not a great choice, and it does seem to be unstable, right? It seems like it'll grow forever, which isn't great. Now, the 15 centimeter fins down here, the oscillations are damped even after the motor burns out. But if you look at the relative positions of the center of mass and the center of pressure on this case, the center of mass and the center of pressure are very close together at the beginning of flight, when there's a lot of mass in the bottom of the rocket because of the unburnt propellant. And you don't necessarily want a case like that, because then any slight adjustments to mass could destabilize your entire rocket, because if you put the center of pressure, in forward, or like above the center of mass, in the rocket, then the rocket will just flip over. It's impossible for it to be stable at that point. Um, so this thing is marginally stable as it is. Yes, making it that way um, results in damped oscillations, but and also just lower weathercocking. So coming off the rail, it doesn't end up going off at as great of an angle from 90 degrees, right? The mean here is lower than the mean for these other cases, but that's not a risk you want to take likely. So probably wouldn't opt for something like this, although you could go for something maybe a bit bigger than that. But for this case, um, we probably want something closer to this 22.8 centimeter fin case, because there's the oscillate or the amplitude of the oscillations doesn't change very much over time after burnout. Um, but you probably wouldn't want to make it any bigger since it seems like it grows a little bit, so you probably wouldn't want the fins to be any bigger than this. So this is sort of the probably around the upper limit of how big you should make the fins. Um, and that's probably what we want for this rocket because we want the fins to be big enough that adjustments to mass distribution and even weird stuff sticking out into the airstream from the top of the rocket won't destabilize the rocket. So if the fins are bigger, stuff like that will have a smaller impact on the stability. Um, but the fins aren't so big that you're going to get these large amplitude um, oscillations later on in the flight. Um, so yeah, the conclusion here is probably something around the 22.8 centimeter fins, and those are in fact what we have on the rocket right now, and they performed fine on the last flight. So we're probably going to stick with something like that. Probably won't make them too much bigger unless we have something really weird going on the rocket that we really need more fin area down low to counteract. Um, so yeah, that's it. Thanks for watching. Um, and sorry the video is so long.